Okay, so today we're going to talk about something that is actually really, really practical, which is compound interest. I don't know if any of you attended there was a talk yesterday given by Linda Davis Taylor and somebody else for the Money Wise Women group. Did you see that? Like at the cafeteria, I think. At 12 o'clock, they gave this talk, like what all women should know for the future. Money Wise. I think basically they were talking about compound interest. So if you missed it, that's okay. We're going to check that out. So the idea is like this. You have a bank, right? And the bank says it has an annual interest rate of R, say. That is like, for example, R could be like 5%. Although if you say no bank gives anything close to 5%. That'd be more like 1%, or maybe less than 1%. Okay, and and you have say P dollars, and you put it in the bank, and you wait for T years. Okay, you wait for T years. And then depending on what they mean by their interest, you'll have a certain money that comes out, and it'll be more than what you put in, right? And so there's sort of there are different ways of calculating how much money you get out, how much money one has after T years. At least theoretically, depends on how the bank compounds it. Okay. This is actually not quite true because I think all banks these days compound in the same way. But there are different things called compound interest, and we'll show you all of them. And then the very last one will be the one that people actually use. Okay. The first few are sort of simple versions leading up to the real thing. Okay. So the first one is so ways of compounding. Okay, you could do something called annual, say that the interest is compounded annually. Okay. You could say that the interest is compounded annually, and what this means is that every year you take your money, and then after 1 year passes, then the money is multiplied by, in this case, 101%. Right? So you multiply the money by 1%, and then you add that stuff on. That's the interest. That's the interest you get. You add that on to it. Okay. So right. So after 1 year, this means that each year the money is multiplied once by 1 plus R. Okay, 1 plus R. So you start off with your money. Your money is P, right? At time 0, your money is P. And after 1 year, so at time 0, T equals 0, you have P. How much money do you have? You have P. At time equals 1, how much do you have? You have P times 1 plus R, right? Right. At time 2, they look at how much money you have in the bank. That's P times 1 plus R, and they multiply that by 1 plus R, right? So you get P 1 plus R, 1 plus R, right? So P 1 plus R squared, right? At the third year, you have P 1 plus R cubed, right? And at the nth year, after n years, like whatever n is, you have P times 1 plus R to the n. Lauren, yeah.
For t equals 0, it's just p, right? It's not money over p.
I just put a money.
Oh, okay.
I just need to say that this is the time,
Oh, okay.
and then this is the money.
Okay.
So I'm making a chart. Okay. Right. So if you start off with $100, say, right, after year 1, you're gonna have $101. Right. If the interest rate is 1%. Okay. After 1 year, you have $101. After 2 years, well, you have 101 times $1.01, right? Is that correct? Right, you have, after, right, if P is 100, right, after 2 years, you have 100 times 1.01 squared dollars, right? Your money at time 2 would be like this. Okay. And after 100 years, you would be dead. But you would have this much money, right? Whatever that is. Okay. Right? Okay, so this is the simplest thing, compounded annually. No bank does this. Okay, no bank does this. But this is sort of a working our way up to the actual thing, the thing that actually happens. Okay. So you can have also something called compounded daily. Compounded daily. Okay. And yes?
What's the thing in parentheses say underneath R?
1%.
Okay.
So let's say, for example, let's say that we're doing, our bank gives us a rate of 1%, which is about what banks give these days. So there's something called daily compounding. Your interest is compounded daily. And so that is that each day, the money is multiplied. You know, your current amount, right? Your current balance is multiplied. How much money you have right then is multiplied by, well, it's not 1 plus R. That would be great, right? If you had a bank like this that said, okay, we'll do in 1 day what the other bank does in 1 year, everybody would go to this bank, right? That would be crazy. And the bank would fail, you know, immediately. Okay, so that would not be reasonable. It does rather this. Okay, it multiplies it by the interest rate divided 365 times, right? Like the rate per day, and then does this 1 time a day. Okay, so in this case, it's like the number of days now. So like after 1 year then, how much money do you have? After 1 year, what should be your money? Well, at time 0, at year 0, so year 0, you have say P dollars. Let's say it's 100, just to make it concrete. You have $100, and then at the end of 1 year, how much do you have, Carolyn?
P times 1 plus R.
P times 1 plus R? Well, not exactly. So think after 1 day, you're going to have this much. After 2 days, you have what?
1 plus R 365 squared.
Squared, right? And then after 365 days, after a year, you'll have this much. Okay, which is different, which is actually not the same thing as 1 plus R. It's actually not the same thing. It actually turns out to be a little bit bigger. Okay, so if you have daily compounding, if the interest rate is R%, and somebody says, I'll compound once per year, and then this other bank says, I'm going to give you the rate, but I'm going to compound daily, actually the daily will give you a slightly bigger number. Okay,
So when you give us one of the compounded daily ones, it's going to ask for T to be in days? Like the
yeah, T would be in days, yeah.
Okay. So, but you could like have given us number of days instead of years.
Yeah,
like
yeah, but I just put it as year to make the comparison with the left.
So you could have given us like 5 days.
Sure.
And moved it to the fifth.
That's right.
Okay.
That's right. Then there would be a 5.
Okay.
Right. So, okay. Okay, does this make sense? So, right, so the formula here would be at day k, one has p1 plus r of b multiplied to the k month. Or I should take all of this. Okay. Okay, so now then there's a third bank. And the third bank says, I am going to compound, I'm not going to compound daily, I'm going to compound every second. Okay. So then if that happened, what would be the formula? Well, you take every second, you would multiply by 1 plus r over how many seconds there are in a year, right? Okay, so let's not do that. But here is, oh no, okay, actually let's do this. This bank says, I'm going to compound, we compound n times per year, n times per year. Okay? And they don't tell you what n is, but they just say n, we compound n times per year. Here's a bank that compounds n times per year. Okay, so, so what's the formula? After 1 year, how much do you have? After 1 year, how much do you have? I'm going to let you guys think about it so just think by analogy, right? If you did it 1 time per year, you have this sort of formula, right? If you did it, maybe I should write it like this. Let me change this one so that it's in years. At year t, one has that many dollars. So that we have analogous formulas. Okay, or I'm sorry, at year n. So here's a formula for the simplest interest. Here's the formula for the daily interest. And suppose you have something that says, okay, every year, we're going to do it n times. So what happens in 1 year? You have your money. How did you think about it for a minute? Okay. Write down something, make a guess, and work for a minute. Talk to somebody next to you. Talk to somebody next to you. You can talk to each other, please. Make friends. You don't want to talk to each other? You don't have to. You don't have to. Maybe people don't like each other. I don't know. It's certainly human nature. Not to like. Kenny, what is it?
Is it?
Oh, you don't guess. Okay, yeah. Hold on.
Okay.
Okay, how many people have guesses? How many people have guesses? Okay, I'll start with Sophie. Sophie, what's yours?
Yeah, take that.
You don't have a guess?
Volunteering that I have a guess.
Okay, you don't have a guess. Sure. Lauren first.
Is it p times 1 plus r and
And Carolyn, what about you?
That's fine.
Okay.
Kind of the same thing, but instead of T, I had N.
Oh, N. Oh, I'm sorry. Wow, this is very bad. Okay, I'm using N for 2 different things. Right? N here is the number of years, and N here is the number of times per year we've compounded. Okay, so let me change this to a compounded k times per year. Okay, and then I think Lauren, yours will change to k here, and then this, let's just say this as t at the time. Right, you divide it by what should it be here? You had an n here and then a t. I changed the n to a k, so this should be a k. Right. Okay. Okay, and k, what did you have?
I would have had a keyword to use.
You would have had a k up here? Okay. Okay, so there are two guesses basically. 1 plus r over t, k to the t. Right, and we're doing it at 1 year, right? So I think this should go on unit 1.
Yeah.
Right? Okay, so here's one guess, and here's another guess. Okay, Carolyn.
Wouldn't the first case, yes, p times 1 plus r over k to the k, isn't that negating it? Because if it's the same time, it should be k times 1, which in this case it would be 1, the increase in 1 year, but it would be like 2k, 3k, because it's compounding however many times, it's not compounding the k times total.
Right, but you just said k, it should be k times 1, which is k.
Right.
So is this, you okay with the k up here?
Yes, just if it's, but only after 1 year. Like
After 1 year, yeah, so after 1 year,
Yes, it would be k, but after 2 years it wouldn't.
it would be
2k.
2k.
Right.
Okay, so this is the right one. Right, right. So after right, you divide the year into k parts, right? Yeah, you divide the year into k parts, right? You divide the year into k parts. Okay, and then at each mark, after each period passes, then you multiply by 1 plus r over k. Right? You divide the interest into k bits, and then you apply those bits of interest at every point, at the end of each period. Right? Right? So after one period, right? Like say this was monthly, right? You divide your 1% interest into 12 parts, and then after 1 month, you multiply 1 plus 1% over 12. After another month, you multiply that by that again. Blah, blah, blah. You do that 12 times per year, right? So you do that 12 times per year. Does that make sense to people? Is that making sense? It's just the same thing that we did over here, right? You take your interest and you divide it into 365 parts, and you do that 365 times in 1 year. Okay, and so if it's k times, well, here's the formula for k times per year, and for an arbitrary year, right, after n years, what you have is this sort of thing, right? K times n, right? Because it happens n years. Right? There'll be nk times nk number of periods in those n years. Like k periods per year and n years. So there'll be nk periods per year. You apply this interest nk times. Is this clear to people? Anyone have any questions? Any questions? Okay, now comes the interesting part. Okay, now comes the really great part, and the part that will make you hopefully say, "Wow." Okay, here it is. Here is the fourth bank, and it is the compound infinitely many times. That's not what they say. It's rather they say compounded continuously. Compounded continuously. No bank says we compound infinitely times. They say we compound continuously. And it turns out what happens is that here's a fact. Okay, so it turns out that the formula formula. Here's the formula. No. I'll give you the amazing fact first. So here's the amazing fact. If you take the limit as k goes to infinity of this thing on the left, 1 plus r over k to the kn. Okay. If you take that to the limit, if you let k go to infinity, these numbers actually tend to something. Do people know? Does anyone know what it is? It involves e.
Sorry.
Okay. Actually, let me, just to be consistent with the book, I'm sorry, let me change this to a t. Okay. So the formula for this bank is that the money at time t is your initial money times e to the kt. So let me put a bunch of zeros. I'm going to put some zeros here to say your initial money. So p is 0. Usually use p sub 0 to indicate the initial money. So maybe the important place to put it is in these formulas. Yeah. Okay, and I'm sorry again, let me change this to a t so that it's consistent with the book. Sorry, this should be R. So these are the formulas for how money grows in a bank, right? These are the formulas for how money grows in a bank. And this last one is the real one that banks use. Okay. The one that banks actually use. So no bank actually compounds annually or daily or n times per year. That doesn't even make sense, right? No bank says we compound n times per year. What is that? Okay. Banks actually use this formula, and that's to say that money in a bank grows at an exponential rate. Money in a bank undergoes exponential, what's called exponential growth. So money bank undergoes what's called exponential growth. Okay. That exponential growth is the same growth that we were talking about earlier, the difference between linear growth and exponential growth. Remember the example about the 2 cents, right? 2 cents growing linearly, that there was one guy who attended every other class, and his money grew linearly. At the end of the semester, he had 30 cents, right? The other person, got money paid to him exponentially, and at the end of the term, had $10 million. Right? So exponential growth is something quite different from linear growth. Okay. Yeah, Lauren?
So in the third example,
Yeah.
why did we use n instead of t?
It should be.
So then all of the t's are for time, right?
T is for time.
Okay.
So I should stick to my notes. So my notes are correct, but when I wrote it on the board, I changed it.
Wait, and then for the,
This one?
yeah,
So T,
No.
just 10.
for like at day k, it was up there somewhere.
I use that one.
Oh, okay, so it should be to t,
Yeah.
p times 1 plus r over 60 to the t. Yeah, okay.
Yes, that one. Okay. So So let me just illustrate, let me give you some numbers to show you what the difference is. Just to make this a bit more concrete, here's an example of $100 at a rate R is 5% and 1 year of time. Okay. In the compounded annually case, well, how much will you have after 1 year? It's obvious. 105, right? After 1 year, you have $105. Right? That's 100 times 1 plus 0.5. Right? Okay. For the compounded daily, so this is the annual guy. The second guy is the daily guy. After 1 year, you'll have 100 times 1 plus 0.5 divided by 365 to the 365. Right? And that turns out to be, that turns out to be $105.15. About that. Okay. So compounded daily is just a little bit better than compounded yearly. Okay. Bank number 4. After 1 year, how much do you have? You have 100 times e to the what?
0.05
0.05
times 1.
times 1.
Yeah.
So e to the 0.05, and that turns out to be, so this one is 0.1267. This one turns out to be 105.1271, something. Okay. So you see that compounding continuously is not all that much better than compounding daily, or practically speaking, it's not all that different. Okay, but this is what people use. In terms of a formula, using the exponential function is easier than every day having to crack some machine. Yes.
But as the numbers get larger, doesn't the difference get greater?
It's true that this tiny amount, it will make some difference, but not
Not a significant amount, really.
well, I mean, it depends on the amount of time that passes. When I was a kid, my dad was involved with a local, like a community bank. And at one point they had this thing where they wanted somebody to run the notices that would be sent out to all the people who had money in the bank. And so my dad said, okay, why don't you write a program that will calculate all the interests for these people. And so I did something, but I think I did it based on like compound interest, like daily compounding, and that was wrong. And of course, I didn't get, I didn't get to do it. I'm not sure how old I was when I say I was a kid. I'm not sure.
What is it, programming a computer program or?
A computer program.
Wow.
Yeah, I should have become a computer programmer. Then I'd probably be retired by now. People, so like I graduated in 91, right? So that was sort of like a great time to be a computer programmer. Many of my friends, or at least a few of my friends, who were computer programmers at that time, just retired after 10 years. So, yeah, that's it. Okay. So so let me just make one comment about language. So notice that the nominal rate was 5%, right? But the effective rate was higher. in phases 2 and 4. Right? After 1 year, you actually got a bit more than 5%. After 1 year, you actually got a little bit more than 5% in both these cases. That's just language. It's not that important. Okay. So what the moral is that that money can be made to grow exponentially, right? Which is what's the moral? The moral is then that you should invest money now, right? You should basically start investing money now, as just put away a little bit of money every year, and allow the power of the exponential function to take effect. Okay, so let me give you an example that I saw on a web page or something, which was that if you 30 years ago, if you had put in $2,000 per year, okay, 30 years ago, $2,000 per year into your pillow, say. Well, then after, right now, how much would you have? Well, you have $60,000, right? But if you put $2,000 a year into the stock market, so into the so-called S&P 500, which is a selection of stocks in the stock market, then now you would have around $300,000. Okay. So, right, and I calculated it just out of interest, just out of curiosity, how much you would have if you, after 20 years, I think the amount is around like $100,000 or so. And then after 30 years, it became like $300,000. So basically, the longer you participate in this, in the curve of the exponential function, the better. Okay? So the moral is, don't go to graduate school. And instead, get a job and invest in the stock market. That is, so if I look at my career, say, I spent a long time in graduate school, and then basically postponed entry into investment, right? Okay, well let's go on to the next subject, and then it'll be clearer why you should not go to graduate school.
I would save a lot of money.
Okay, actually you would make a lot of money. Okay, so continuously compounded interest. Okay, the formula that we just figured out is that the amount of money you have at time t is the initial amount times e to the rt, where r is the nominal rate, nominal annual rate. Okay. Now we're going to introduce a concept called the doubling time. Okay. Doubling time. How long does it take for your money to double? How long until my money doubles? And when you get older, this is something you think about all the time. How long until my money doubles? Okay. Because you think about retirement, basically. And you think, okay, I've got X number of years, let's say 30 years left to retirement. And then you say, okay, will I have enough money at that time? So you have to think, okay, what's the doubling time? How long until my money doubles? What approximately should I expect to have, and am I saving enough? Right? So this is how you calculate it. Right? This is one way of starting to think about it. Or this is the beginning of how to think about it. Okay. So how long until your money doubles? Right? How long until your money doubles? You can figure it out. Okay? If you know, let's say that say that R is 5%. Okay. Say R is 5%, and you ask, how long until my money doubles? Okay. So we can figure it out. Right? We can figure it out. We say, what do we want? We want to know T such that P of T is twice my initial amount. Right? So what do you do? Right? You know that the amount of money you have at time t is P naught e to the RT, and you're wondering when does that equal 2P naught? Okay. For what t is P naught e to the RT equal to 2P naught? Well, take a minute and figure it out. Maybe let me put 0.05 in here, since we're taking R to be 0.05. Okay.
I still don't get it. I already have that 0 at the base of P again. It's like we were starting out with, right?
Oh, P naught just denotes the initial amount, and so P naught is initial money, like how much you put in at the beginning. You put this money into the bank, and you just leave it there, and you're wondering, I wonder when it's going to double. Okay, who has the answer? So,
T equals natural log of 2 over 0.05.
is that right? I'm not sure. Let's work it out.
I got natural log of P naught over 0.05.
Let's work it out. Let's work it out. Okay, so what do we do? Maybe the first thing we do, we can divide those signs by P naught. Right? Right, divide those signs by P naught. So we're looking for the T for which e to the 0.05 times t is equal to 2. Right? Then you take the natural log, so you get 0.05 times t is equal to natural log of 2. Oh yeah, you're right, so you get natural log of 2 divided by 0.05. Does anyone have a calculator? You do.
Natural log of 2 divided by 0.05.
Yes, please.
13.863.
13.863. Okay, so in 13 years, however much money you put in is going to double. Lauren?
So for, just to make sure, the P to 0, or P naught E 0.05 T equals 2P naught, that's like the, except the 0.05, that's like the formula to figure this out.
Yeah,
Okay.
right. I mean, just think, what does it say in English, right? At what time does my money turn into double the initial money, right?
So can we do that with like tripling and stuff too? You just change.
Yeah, then the 2 become a 3, right? 2 become a 3. Very good, right? So just translate, as long as you can read this in English, then you know what the purpose of this is. right? Or as long as you can say the thing in English, you can translate it to a formula. You can say, I'm wondering at what point the money I have at that time equals double my initial money. And then you just solve. Right? You just solve for t, and you say, okay, my money with a rate of 5% interest, after around 14 years, my money will double. And then after another 14 years, my money will double again. After another 14 years, my money will double again, et cetera, et cetera. Okay. So this is actually goes to the point of don't go to graduate school, because if you go to graduate school, who knows? Maybe it takes you 14 years. Say. I hopefully not. Suppose you spend 14 years in graduate school. What does that mean? That means that you missed out entirely on one doubling cycle. In other words, your money will be half of what it could have been. Right? In some sense, this is sort of an exaggeration, but because graduate school maybe gives you a better salary, or who knows. But if you spend too long in graduate school, you sort of miss out on one doubling cycle, and then you have to maybe make up for it by staying working an extra 14 years or something at the end to make up for that doubling cycle that you missed. Anyway.
Can you do this with decay?
Same thing for decay. Right? Same thing for decay. Shall we do it? Why not? Okay. So is everyone okay with this notion of the doubling time, right? Somebody gives you a rate of growth and says, how long does it take for your whatever it is to double, your population to double, for example? The population is growing exponentially at a certain rate. How long does it take until the population doubles? That's also an important question. Right? The world populations tend to grow at an exponential rate until the food starts running out. Right? At which point then the rate changes. So it's not really an exponential function. It's actually, you have to throw in some other factors. You have to include the food actually. But anyway, you have to worry, when is the population? If the population is growing exponentially, what's going to happen? When is it going to double? Let me make one observation, a question. Did this depend on P naught? Did this time depend on P naught? It didn't, right? So whoever, no matter how much money you put in, it just depended on the rate of growth. Right? So if you had $1 million, after 14 years you have $2 million. If you put in $100, after 14 years you have $200. Okay. So there's sort of a analogous thing, which is called maybe you could call it the halving time, right? Or the half. This is also sometimes related to something called half-life. Okay. So you have, suppose you have something and it is decaying at a certain rate. It's decaying at an exponential rate. So for example, radioactive materials. This is a standard example. Radioactive materials decay at an exponential rate. Okay, so that is that their growth, the way they grow, and let's just say A for amount, the amount of time t is the initial amount times e to the kt. But k here is a negative number. K here is a negative number. Okay, so this is a negative exponential function. It's a decaying function. So this is the decay constant. Okay, yeah, Laura.
K is the same as R, right?
K is the same as R. Yeah. If you want me to call it R, I'll call it R.
No, I'm just making sure.
I'll call it R. Because it's basically the same thing, except it's negative. Okay. So you can ask the same question, right? If you know the decay constant, well, when does, after how long are you going to have half the material? Right? how long until I have only half of what I started with. How long until I have only half of what I started with, right? Because that's a concern, right? Maybe you like to have a certain amount of you need a certain amount of radioactive material, but it's decaying really fast, okay? Right? And so you need to figure this thing out. Okay, so what do you think we're going to do to figure out how long until half of it is gone? To figure out the half-life? The same thing, right? So you just ask, what's the question? We are asking, at what t does what? A naught E R T equal what?
1/2.
1/2 of naught.
Yeah,
1/2 of A naught, right? At what time does the amount that I have equal half of the amount that I initially started off with? Right? Math as English. Okay. And we play the same game, so we just calculate, right? Calculate or solve for t. Solve for t, then p to the by t equals 1/2. Right? Take the natural logs of both sides again, you get RT equals natural log of 1/2. That is to say, negative natural log of 2. Okay? And then T is going to be negative natural log of 2 over R. Okay? So it's going to be at that time that we have half the amount. Notice that R is a negative number, so this makes sense, that you get a positive number as your time, your half-life. So this is the time when half is gone. This is the so-called half-life of the material. And next time what we'll see is that we can actually go the other way. If somebody gives you it's probably obvious, right? If somebody gives you the half-life, then you can figure out the rate. Right? You can figure out the rate, you can figure out the R. Here it is. Right? R is just going to be negative natural log over 2 over t. Over the t being the half-life. Right? And so you can go backwards. And we'll play, there'll be various problems which are just sort of like, if you have the rate, tell me how much you have at this point in time. Or, I give you only the half-life. Can you tell me how much you have at this point in time? Well, sure. You figure out the rate first, and then you figure out how much you have at that point in time. Yeah.
So the negative just comes from us going to the negative?
No. The negative comes from, there are two negatives. One is the natural log of 1 over 2. That's negative the natural log of 2. The other negative is because we know this is decaying. Right? This is a decreasing exponential function. So the exponent is negative. Okay, that's it for today.